Hello, everybody. My name is Daniel Klimuk, and I am Zarhus team leader, embedded and Linux enthusiast. Currently working in ChamDev, of course. My presentation will be about RAM-wide software solution. More about it on the next slide. The agenda is following. The RAM-wide, a solution against RAM attacks. That is about RAM-wide, RAM attacks, warm boot attack, with cold boot attacks, a short introduction to those attacks needed for our case. Then we are going to look into RAM wipe in details because it will be needed for the conclusions. So RAM wipe structure and workflow, RAM wipe testing environment and methodology, RAM wipe testing results, then conclusions and questions and answers. So what is RAM wipe? RAM wipe is a fully software solution based on Linux executables, shell scripts, Dracat, and its modules. It was developed by Kicksecure, is open source, is under RGPL license, and currently is in testing stage. It is one of the first solutions which provides which has a goal to mitigate RAM attacks, more precisely cold boot attacks, based on Linux tools. What are those warm boot and cold boot attack, and how they differ? It is very important in our case and will influence the final conclusions. Here are the two diagrams that are showing the attacks, their workflow. They have a very big and common part that is first booting stage, when the platform goes from no power stage to firmware or bootloader, or firmware and bootloader, then it boots victim's OS. And the victim's OS is performing some operations on secrets, for example, LUKS partition, decryption, encryption, any key management, any signing, other encryption of packets, for example, that will be sent over the network, etc., etc. Then the victim's OS it may leave those secrets in RAM. It may clear the secrets in RAM, but then it's shut down. The way the system is being shut down, I can draw it right here. This is the place where it differs for these two attacks. In the warm boot attack, the system is being shut down without breaking software execution. That is, you are just typing in Linux console system control power off, and Linux and all software is shutting down. Entire process is being executed, software process. This is this is a prerequisite for a warm boot attack. That is, we are, for example, doing a reboot, system control reboot, and then we are booting without turning off the power. We are booting back to firmware bootloader, and then we are booting attacker's OS or application. This application will do the attack. It will search the RAM, it will dump the RAM wherever. It will check out on our secrets in RAM. In cold boot, the main difference here is that we are breaking the software execution flow. There are a lot of ways we can do it, but when we are breaking it and then booting the platform again, the RAM that was previously used by victims OS still contains or might contain. It may differ because real physical RAM might lose its values, but more about it later. But let's assume it does not lose its values, so it contains the values, the secrets, the code that was executed before, and when we are booting from this state to firmware bootloader, of course, firmware bootloader will overwrite some addresses, but not all, and then we are booting to attacker app. Attacker application will have access to what has been executing before we break its flow. So if here, as we will talk about later, during power off or reboot software execution flow, something will clear the RAM, the attacker's application that will be booted after such a reboot or power off will not have access to values that were previously in the RAM. But here we are breaking the execution flow, and something that will clear the RAM will not be executed during power off, and the attacker will have access. This is the main difference here. Right now, let's talk about the RAM wipe. RAM wipe, as I was said, is relying on Linux tools and executables, and more precisely, it relies on Dracat, that is Dracat in ItRamFS, Dracat system DM, modules, services, and RAM wipe scripts to do its work. The work of the goal of RAM wipe, as I said, is to protect against or mitigate cold boot attacks, as well as warm boot attacks. How the RAM wipe does it? Firstly, going from no power state, we are loading as I was said before, firmware and bootloaders, and we are loading the victim's OS, for example, Linux kernel. Then we are getting to RAM disk in its RAMFS that was prepared by Dracat. We are launching init processes, and then the Dracat hooks start. Some hooks trigger some of the RAM wipes scripts. At the boot process, we are only preparing to launch RAM wipe. It does not clean wipes or manipulates values in RAM. It's only preparing, it's checking Linux kernel boot parameters and thinking, should I start? Should I clean something later? After we check everything, we prepared everything. We're getting back to Dracat hooks, and at the end we are getting back, not getting back, but putting to root and rootfs. Here we are in rootfs already. Our OS is doing something. Our apps manipulating secrets, downloading something, whatever. And then we want to shut the system down, power off it. We're typing system control reboot, system control power off, and then some system there services are being activated, launched, and they activate RAM wipe sequence. RAM wipe still checks kernel boot parameters. It prepares its stage that will be launched later. For execution, it checks whether it should execute all its stages or only one stage. What stage exactly? We'll talk later. Yep, and then we're getting here. It's a place where Dracat restores RAM disk, so we're getting back to this minimal file system that were used during boot. And we're here. We're inside our RAM disk. And yet again, some Dracat starts, or more precisely, Dracat hooks are being executed. These Dracat hooks trigger the first run wipe stage that still checks some boot parameters, and then here we are manipulating actually memory. This stage is called first run wipe stage. Then comes the second, of course. As the first stage uses SDM in its script to zero out all memory, or at least all memory what is available for run wipe. These two arguments are for one step that fills RAM by zeros, and the final argument is for verbose output. Then it checks. Then it prepares kernel execute. Kernel execute will fail if we previously during boot, if runway previously during boot decided that no, we are not executing, for example, second stage, because kernel execute, exactly this command, is dependent on kernel execute load. If kernel execute load was not executed, then this will not be executed, and the second stage will not be done. To the second stage, and the second stage via kernel execute command will load again our kernel, and then it will get into RAM disk, and then it will start Dracat hooks again. Still, these Dracat hooks checking whether something should be done or should not be done based on Linux kernel command line parameters. This is exactly where I'm pegs it. Then it does one color. Okay, here. It does the second wipe again with the same command. And after it just shutdowns or reboots or whatever process you choose before in rootfs, for example, power off the system. That is entire run wipe. Only two stages, the same command and the same tools, just executed several times. And we wanted to test it. This is our test methodology. Actually, it's the same image because it explains a lot. Actually, we are being an attacker here. We prepared an application that is being loaded from Dasharo firmware, an A5 application that dumps entire memory RAM that was not modified by firmware, because firmware, as I said, still modifies something, and we don't want to check those values. They are useless from our point of view here. The exact test methodology is firstly to make sure that dumped RAM will not contain any firmware data. We are doing it on here first stage. Then we are going to booting all needed software up to the bind Trixie, which is used here with installed RAM wipe. And here the testing scenarios for these two attacks differ. On the first attack, we are doing system control reboot to get back to firmware and boot our applications that will dump memory. And here we are resetting the system. the platform. More about it later, which platform and how. And getting back to the Shara firmware and booting car up. So here, the run wipe is being executed, and here, run wipe is not being executed because run wipe, as I said lately, relies on software execution. It gets from rootfs into initramfs, then into new kernel. And the test cases were manually or via automated tools were checking what memory was zeroed, what memory was not zeroed, and checking what exactly is in this memory, like kernel data, kernel code, bootloader code, maybe some processes. There sure were some processes, for example, systemd, and then real world attack on Lux system just to try to dump its case and get to Lux partition. And the testing results. I will explain the results in brief because there are a lot of results. There is a lot to say here, and this will be said in our blog post that will be published soon, probably this week. Maybe today, maybe tomorrow. Just make sure to follow our page, FreeMDeb on LinkedIn and me on LinkedIn too. I will repost it, of course. But the quick results are as follows. The run wipe did not zero out some memory regions. It did not zero out Linux kernel. It did not zero out grep addresses. It did not zero out the processes address space that were executing during the time when run wipe were zeroing out the memory. It did zero out the memory that was not used by any processes or Linux kernel or grep. So it did get rid of leftovers in RAM. And for warm boot attack, we did not dump any Lux keys from memory, from RAM. It might be a success here. But for cold boot attack, because of the fact that run wipe relies on software execution, and during cold boot attack, we break the software execution. Nothing was zeroed out, and we were able to dump Lux keys and get to encrypted Lux partition. And the more general conclusions, run wipe cannot wipe memory that is used. You can even see during the wipe stages that you will get out of memory killer for ZDM. This is because run wipe trying to zero out memory that is not assigned to it. It is limited by operating system, and that is. This is a problem because you cannot just launch run wipe and say it is secure, nothing will get out, nothing will be stolen. You should make sure that run wipe will and have wipe your secrets from RAM. And during cold boot attacks, there is no protection from cold boot attacks because run wipe didn't even execute. These are the brief and quick conclusions. You can check the more detailed and described conclusions, as I said, in our blog post.
Yeah, thank you, Daniel. I guess like maybe we have some questions. I don't know, Aaron, Patrick, do you have any questions? I guess like from my side, what is important is like of course you focused on the things that are not happening. but there is like very little focus on things that really happen and what's the positive side of the like. So we have like a lot of fear of missing out, but we have not much praising of what positive happened. So what positive happened is that for the area of the memory which is wiped right now, which is not under control of the kernel or bootloader, we really wiping the Lux keys. Yeah, so that's benefit of RAM wipe. So if we compare the system without RAM wipe and with the RAM wipe, we essentially are in better shape than. Am I correct, or this is like, am I deluding myself?
Definitely.
Yeah. So that's very important to highlight that really when we compare system without RAM wipe and system with RAM wipe, we are in better shape. So and this shape is better by the fact that that the area in which Lux key was kept is cleaned. The problem is, what if something will happen in the areas, in the areas like the Linux kernel or some executed process areas or something. Okay, I see a question from Aaron. One question or more of a statement from me. The kexec second stage should allow wiping memory used by applications that were running when the system was shut down. It should also theoretically allow wiping kernel memory, assuming that the kexec kernel doesn't allocate memory without initialization, which is not necessarily a correct assumption, but if it does that, it should be able to reach pretty far when wiping things. Yeah, I agree. I guess, like, Daniel, do you have any comments to that? Can you kind of something?
I do agree. If some processes were executed before the second stage in some memory, and the second kernel does not allocate anything in this memory, or its processes is not executing in its memory, it will be wiped because nothing controls this memory.
So I guess this is like a definitely good next step and something that could be improved, could be fixed, and it will make RAM wipe even better. Despite the limitation that we should be aware of, that there is like certain limitation that we will not, work around. There is like, skull boot stuff. And that's fine. And I guess that's fine because the problem of improving the security of the systems is not that we have one solution which suddenly kill all the possible threats. We working on moving the stage to better place. We working on improving the environment step by step. Sometimes, like, someone said at some point that the feedback is more important than planning, and I agree with that. And thanks to this feedback, thanks to the very quick feedback loop, we improve the ecosystem, because it's very hard to at the beginning create holistically correct system. Yeah. Right. We need to improve our documentation. RAM wipe absolutely requires a clean shutdown. It cannot protect against hard power off and freeze RAM original code boot attack. It operates under the assumption that the shutdown the system and RAM is wiped. Yeah. So that's very good. I have some ideas how this could be potentially mitigated. There are some. Yeah, you could for example, have some protection inside BIOS when this is. But then you have to trust BIOS, and that's the problem, because most of the platforms will not have trustworthy BIOS. So yeah. So I guess that's some limitation.